Okay. So what this is saying is that the inverse Laplace transform of e to the at times some function f of t is nothing but f of s, and then you shift it by an amount a. That's what this is saying. It's a very powerful definition for s greater than some alpha plus a. Okay. If the Laplace exists for some s greater than alpha for f of s. Okay.
All right.
And so an example on that would be like this here. This enables you to shift things. Like say, if f of t, like here, number 3, okay, is t e to the 2t. No? So as soon as you see an exponential, you know that this is a Laplace that is shifted.
Yeah.
So your f of s here or f of t here is just the t. No? And you can easily figure out what Laplace of this is. We did this on the previous section. You can use the definition.
Yeah.
Or you could use the tables. Right?
Yeah.
And when we used the definition on the last section, we did integration by parts because we let's actually do it. So because this is a fairly quick one. So this is the integral from 0 to infinity of e to the minus st times t dt. Okay. So integration by parts once gets you there. So integration by parts. So u is what? U is t. dv is e to the minus st. So du will be dt, and v will be e to the minus st over negative s, right? And integration by parts says that the integral of u dv is equal to uv minus the integral of v du. You understand that?
So yeah.
Okay, so then coming back to the continuing on integration by parts, so uv, so this will be t e to the minus st over minus s minus v du. So minus, and there's a minus s here, so this becomes 1 over s integral v du, so e to the minus st dt. And we can easily integrate this, so we get t e to the minus st over minus s. The integral of this is just e to the minus st over minus s, and you have another s here, so this becomes minus s squared. And now we will evaluate from 0 to b, and then we will take the limit as b goes to infinity. Again, this is giving you more practice on using the definition of Laplace to figure out Laplace. Okay, plug it in. So you get b e to the minus bt, I mean bs, right? Over minus s. This is for the b, minus e to the minus sb over s squared. That's the upper bound. The lower bound, this will be 0 because t is 0. And the second one will be minus 1 over s squared. Okay? And now we will take the limit as b goes to infinity. Now I can bring this down, and this becomes minus 1 over s b over e to the bs. Now, as long as, and then I can take the limit of this as b goes to infinity, and then the same exact thing on the next one. So this becomes 1 over s squared e to the sb. Okay? Plus 1 over s squared, which is coming from here. Now, as long as b is greater than, or s is greater than 0, those two limits go to 0. Because the exponential part grows much faster than the b as b goes to infinity, and this goes to 0, and this goes to 0, as long as s is greater than 0. And that's why here we said, when we started the theorem, that as long as s is greater than alpha in the original Laplace, in this case our alpha is 0. Okay, so s greater than 0. So then the first two limits vanish, and the answer is just 1 over s squared. So therefore, the Laplace of, we're trying to find the Laplace of t, okay, is turned out to be 1 over s squared. And what does the theorem say? The theorem says if you have an exponential, right? What was our original question? Our original question was e to the 2t times t.
Yeah.
So what this theorem tells you, it's the same as the Laplace of t, which we found, except you replace the s with s minus a. What's a? A is 2, the exponent of e. So this will be the same as this, except instead of s, you use s minus 2 squared. And instead of s being greater than 0 here, for the domain, s has to be greater than 2. That's why we stated in the theorem in green here that it has to be greater than alpha plus a. So 0 plus 2 is 2. Okay? So this enables us to find the Laplace of this. That's how you use this. This is a fairly important theorem.
All right.
Okay. Why don't you try one here, yeah? You could try, so 2 and 4 are related. Let's do 2, and once we have 2, we automatically have 4. Right?